Yes. So welcome to all of you. And my name is Van Lequi. I'm a senior data scientist at Envoy University. I'm actually in the Cloudia special unit that handle data science, data management, and infrastructures support, in-depth support for researchers and students at Envoy University, Denmark. And this webinar and also the whole series is mainly organized by Envoy University and NVIDIA. We co-organize this series. It can be webinar, or later when the condition allowed, we also organize workshop to deliver the hot topics in AI, and that is aimed to facilitate the collaborations and knowledge sharing within Envoy University and between Envoy University and NVIDIA, and also between Envoy University and the rest of the world. And I think Jonny is coming in soon. So
I'm here.
Get started. So if you have, hi Jonny, you are in now. Yeah. Maybe I need to get my earphone on. So if you have any questions, feel free to ask in the chat of the Zoom, and then I will monitor and send to or read it for Jonny later. Yes, so a bit introduction about Jonny. He is a senior data scientist in the healthcare team at NVIDIA, specializing in the application of deep learning and machine learning to medical imaging. Jonny works with customers and partners to find optimal solution to their AI training and deployment challenges, mainly in the field of computational pathology. Jonny's background is in software development, having been CTO of a data automation company working in the healthcare domain. And I am personally very happy to have you here today, Jonny. It is a very interesting topic, and we have a lot of people signing up or signed up for this event. So the screen is yours, Jonny.
I think you need to give me permission.
Yeah, I will stop sharing and then please
okay.
Go ahead. Yeah.
Okay, can you see my screen and hear me okay?
Yes. Yes.
Great.
Yeah.
Great. Well, thank you very much for the introduction. It's good to be here today, albeit virtually.
Yeah.
Hopefully it won't be too long before we can get back to face-to-face things, because yeah, it's not quite the same. But anyway, I will do my best to you know, it would be nice if this is interactive. So if you do have some questions, please feel free to, you know, come off mute and ask, or you can type something in the chat. The only thing is, I think, Bang, you'll probably have to read those out, because I can't actually see the chat whilst I'm presenting, whilst I'm showing my screen for some reason.
I'll do that.
Okay, great. Otherwise, you know, feel free to ask questions at the end. That's fine too. Whatever works. Okay, so yeah, I'm going to sort of, I'm always conscious that when you do these talks, there are people, you know, varying levels of expertise and knowledge on this, and so, you know, I should probably caveat up front that I probably won't please everybody here, but I'm going to try and go over some basics. I'm not going to spend too long on that because I'm sure there are plenty of you who probably know those basics. But I think it's, to get a good understanding of, some of the latest techniques, you kind of need to understand a little bit about some of the sort of fundamental algorithms, which is why I'm just going to sort of recap over that. So this is the agenda that I'm going to cover. So I want to talk a little bit about, sort of very, very briefly, just about NVIDIA, its sort of history and why, we're in this situation we are. And then, as I say, a kind of quick summary of AI. And like I said, I want to just cover these fundamentals of deep learning algorithms, because I think it's helpful just to frame the sort of, some of the latest stuff I'm going to talk about. One of which is federated learning, so I'll talk a little bit about that. I think it's a very interesting topic. And, the world is not all sort of rosy and AI doesn't solve anything. So I think it's important to mention some of the challenges that exist as well. I'll talk about, some of the latest tools, and then I'm going to just quickly show how to sort of get started. There are lots of different ways, obviously, but if we have time, I might even do a very, very sort of brief demo of sort of training a network. So that's what I'm going to do. Hopefully there's something in there for everybody somewhere along the line. Okay. So first question, NVIDIA often gets asked, although these days that has changed a bit. Our reputation has gone beyond gaming. But when I first joined, I'd go to a conference or something, people say, "What, why is this gaming company at a healthcare conference?" And obviously, there are a number of reasons for that. I mean, yes, NVIDIA was a gaming company, as probably many of you know. Graphics was where we started in sort of early 90s. But GPUs have really evolved. I mean, in the first days of graphics, of course, there were no dedicated GPUs. They were just part of the sort of computation of the computer. And NVIDIA were one of the first people to realize that there was scope to have a dedicated piece of hardware. But they've come a long way, since then. I mean, initially, interestingly, I think the first version that NVIDIA released actually used a slightly different technique. Rather than using triangles, rasterizing, using everything with triangles, they actually used rectangles, which is actually quite a bad idea for a number of reasons, and they abandoned it fairly quickly. Which is, but I think that sums up NVIDIA in many ways. They've always been very nimble and agile and willing to adapt. And one of those, adaptations was, seeing that actually, these GPUs, which are now standard part of the data center, things weren't always like that. And just having that sort of vision to see, okay, it seems that this computation is needed in other spaces other than just gaming. So that's really sort of what, where this came from. The other thing that we quite often get, whenever there's AI in any talk, of course, you always get this, AI isn't that sort of dangerous. People are sort of scared of the unknown side of it, and think of sort of scary sci-fi films and killer robots and all this sort of stuff. And obviously the press love those sorts of things as well. But the reality is that AI is just a tool. I mean, a knife or a screwdriver can be dangerous, but if it's put to good use, it's perfectly safe. And AI is no different from any other. If it's if it's misused, it can be dangerous. If it's not, it's benign. So just get those things out of the way. So yeah, I mean, what going a little bit deeper, I mean, what does gaming have in common with deep learning? And it's quite simple. It is kind of the amount of computation. Both of them are really computationally intensive, and the advent of GPU, well, sort of things like deep learning were really started when some people started using GPUs, sort of hacking them almost, to use them for other things. And in fact, when people first started doing that, again, NVIDIA realized that there was a demand for actually using these for something else. So they created CUDA, which is, our sort of GPU programming language. And then, of course, this demand for GPU computing has really arisen from the fact that Moore's law is just not delivering, faster CPUs anymore, which it used to. But of course, the demand for more computing just carries on endlessly. The other thing, of course, is that deep learning is not, it's not a sort of new thing. It's been around for a while, and people don't appreciate actually just how prevalent it is. It's not just, I mean, there are one or two industries that I guess get all the kind of exciting attention, for which AI is not necessarily sort of mature yet, but there's a lot more mundane things for which things like recommender systems, which are used all over Netflix and the internet, that they use AI algorithms. They use a lot of machine learning, and that's why many search capabilities are a lot more sophisticated than they used to be. There's all sorts of stuff going on. I mean, Facebook have a deep face feature that creates a 3D model of your face from online photos and can adjust for lighting and facial expressions, and has extremely high accuracy at recognizing you in other, in other photos on the internet, which is, there's all sorts of examples of this, this sort of technology around. Okay, so that just gives you a sort of brief overview of the sort of NVIDIA side of things and where it came from, and a bit of deep learning. So let's just talk a little bit more about sort of AI and what we mean by that, as well, and where it sort of where this came from. Various sort of definitions of artificial intelligence that are out there, and of course, it encompasses a lot of different things, and it means different things to different people. But it's not the best term in the world, really, artificial intelligence. But we're kind of stuck with it. So, the photo in the background here is actually Frank Rosenblatt fiddling around with some connections in some early AI, and although it wasn't terribly kind of sophisticated. And at the time, there's a lot of hype, and actually they were on the right track, but there were several limitations which were just very difficult for them to overcome at the time. One of which was just the fact that they only used a single layer of these networks. Had they strung together more layers, they would have had a lot more success. They just didn't really realize that at the time. Yeah, and then of course, as we all know, the artificial intelligence is, it's not just about deep learning. It also includes machine learning, which kind of has been around for a little bit longer. And machine learning is probably still the majority of what we call AI today. Standard sort of machine learning. Deep learning tends to be used in, I suppose it really sort of took off in image and computer vision. But language is the other really massive kind of use case today, and I'm going to talk a little bit about that too. And then, of course, there are several breakthroughs along the way that really kind of launched deep learning in particular success. So, recognizing digits. What was interesting about that was, just how good convolutional networks are at dealing with handwritten digits compared to other classical machine learning techniques. And like I say, if I've got time, I'll just do a quick demo of training a network on this. And then the other thing which really kind of made deep learning stratospheric, and convolutional neural networks in particular, was ImageNet. And in 2014, well, 2012 was the first time when AlexNet was used and beat the rest of the competition by such a sort of huge margin that people really sort of stood up and took notice. But I think also important was, you know, in 2014, and you know, between 2014 and 2015, when essentially, you know, we surpassed the human ability to recognize images, you know, these internet images, and that was quite a sort of breakthrough, this so-called superhuman performance. And we've seen this, you know, over the years in all sorts of other, some of them supposedly, you know, impossible for sort of computers to beat humans at, but it just, you know, it just keeps going and going, and the frequency with which these achievements are accomplished, it seems to be increasing. And of course, you know, recently we had the AlphaFold stuff, which is pretty amazing. So, but what do, you know, what do we actually need? What's the sort of fundamental stuff we need for you know, for machine learning, deep neural networks? And you know, I'm sure most of you know this. We need the data, we need the network, and we need some sort of feedback mechanism for the training. And typically the way we do this, you know, we train it by providing data to the network, you know, so that might be ingesting images. The data flows through this network, and then we output some sort of prediction. And so the feedback we provide from the expected sort of label. So if, you know, if we're predicting a dog or a cat, we obviously need to flow back that information as to whether it was kind of right or wrong, or to what degree it was right or wrong, and then update the network. And this, you know, this is the loop that sort of, you know, drives most of this stuff. And what do we do with it? Well, in healthcare, we you know, there's a number of different problems that, or types of problem that we can solve with it. So, you know, detection is something there. Classification, you know, what type of thing is it? Segmentation, so where is it? You know, prediction, so you know, looking at an image and then saying how long is somebody likely to survive, or recommendations. So, you know, what treatments tend to have proved successful for an image, you know, electronic healthcare record such as the one we're seeing here. So these are the sorts of problems that, you know, that we try and solve, not just in healthcare but other industries too. Yeah, this just kind of shows again a little bit more about the sort of, you know, classification, just applying a label to an image, detection, maybe, you know, predicting a bounding box, and then segmentation, which is actually classifying the pixels in the image. And this is really just showing how it contrasts with, you know, classical approaches to you know, computer vision. So, you know, previous to deep learning, you would need some sort of domain expert, well, particularly for things like healthcare, to be able to tell you, you know, as a computer programmer, which features are important in, let's say, the recognition of a car or in the recognition of a tumor. And, you know, it might be, oh, right, yeah, you need to look for these ellipses that are going to be the wheels. If you see those, then, you know, chances are it could be a car. Now, of course, with deep learning, we don't need to do that. We just need to provide labels and provide those input images or data, whatever it is, and then the network will learn its own features. So we do the training, and then when we've trained the network, we then are ready to deploy that network in the real world, at which point the network is not updating its weights, it's just making predictions using those trained weights. Okay. So yeah, apologies for bits of that you've probably all heard a few times before, but I think it's good just to sort of level set.
Jonny,
yeah,
there's a question in the chat. Shall I put?
Yeah, please do.
Now?
Yeah.
In the two previous slides where you have classification and prediction slides, so on.
Yeah.
There's a questions asked. Can we develop one AI tool for more than one task? Like,
yes, good. Yeah, good question. Yeah. So yes, absolutely. I mean, And this happens quite a lot now. So, for example, in pathology, there are a number of sort of networks that are out there that will. So, one of the big tasks to get in pathology is spotting nuclei that are in the process of, so cell nuclei, in the tissue that are in the process of dividing, so mitosis. And a typical task you might have there is, you provide a whole slide image, and then you ask it to find all these nuclei and then classify them as well. So the output from a network like that would be, a segmentation mask. So where all the nuclei are. And then maybe, they'll be color coded or something to indicate what type of nuclei they are, whether it's currently dividing or whether it's not, and maybe some other sort of type of information. So, and essentially there are various parts of the deep learning network that you can, customize to stitch together all sorts of different types of tasks into one network. Or alternatively, you can have, two networks that are working in parallel to do different things. There are benefits in both approaches, but these days more and more we're seeing, yes, quite complicated deep learning sort of network architectures that do more than one thing. And what's interesting about that actually is, but previously these, two things that might have been considered different tasks, like classification and detection, when you think about it, there are features in those images that are important for both of those tasks. So what people often do is teach a network to do both of those things simultaneously. So it will learn, two sets of outputs, but it will learn them from the same set of features. So hope that answers the question, and I will explain that actually in a couple of slides time. Okay, so in terms of deep learning algorithms, the one which I mentioned before has been around for a long time, and this is what that guy was fiddling around with, is this perceptron, which is really simple idea. So this is the sort of artificial neuron, if you like, developed by McCulloch and Pitts in way back in 1943, and Marvin Minsky in sort of 69, then carried on, did some more work on this. There's also, and that in turn was actually grounded on neurological work, which was done even earlier. But essentially we have a number of inputs which are numerical values typically. We sum them together, and then we have some sort of threshold function. So those inputs could be, from sensors, they could be pixel intensities, could be anything. And the way that we learn more complex functions is by chaining more of these together. This is where you get this multi-layer perceptron. So we've got, inputs, they might be an image, it could be anything really. And you chain together some of these, perceptrons, and then you have an output at the other end. So in this particular case, we're making a prediction as to whether something is, it belongs to class 1 or class 2. And by training the network, we're adjusting the sort of weights, because that's one of the things about this perceptron is that so when we do this, this summing, we're weighting those inputs, so we're multiplying those inputs by some learned values. That's the kind of key to this. And there's also bias as well, but let's not worry about that too much. So these multi-layer perceptrons can do pretty sophisticated things. The problem with them is really just that then for images, they're not very memory efficient, because every single pixel has to have a sort of a weight associated with it. And if you start chaining a few of these layers together, you run out of memory quite quickly. So for that reason, people started, seeing, well, how can we sort of slim this down a bit? And one of the really effective ways of doing that is this convolution process. So convolution is kind of used for other things, but essentially, if you imagine the purple as being your input image, the purple on the top left, and then you multiply it by in this case, a 3x3 pixel filter. So just think of this as a multiplication between the input and this filter. And essentially, all you're doing is just stepping over the input, multiplying it by a number of filters to generate some output. That is all convolution does. The reason why it's so effective is because the weights, rather than being associated with each of the input pixels, and now they just belong to these filters. So the 3x3 is example of a set of filters that we're applying. So we slide this over our input and then do this multiplication, and then we usually apply some sort of activation function that just gives it some sort of non-linearity, and that's really important for learning complex functions. And that might be some sort of sigmoid function or something. And then so I'm just going to get rid of the reboot software reboot window that's popped up. I've got another 2 hours left, so we should be all right. So we and what this does essentially is it gets rid of the need to have loads and loads of weights, because we share the weights. For every input pixel, we're applying the same filter over it. So it's not necessarily better than the multi-layer perceptron, but it's much more practical and effective, because it reduces the memory consumption. And the other thing which really is really kind of interesting and good to understand about this is how the different layers work together. So if you imagine, we've got all these different layers, what you can see there is that on the left is some sort of input image. Then we have these are the filters. It's just a graphical indication of the sorts of filters that are learned at the lowest layer. So they're typically sort of text, things like sort of vertical and horizontal lines. So very sort of primitive, edges, that sort of stuff. And as you go up the sort of chain of these convolution operations, we tend to reduce the kind of spatial information. So we're looking at sort of bigger features and more abstract features. So we build up from edges into textures into sort of small features like maybe an eye or a mouth, and then by the end of it we're up to sort of full faces. And then what we tend to do once we've learned all these different features is we then remove all the spatial information and then just feed it back into one of those multi-layer perceptrons we had before to do the classification or whatever it is. So we have these, and these are these fully connected layers they're called. But going back to that question that was asked before, not sure why there's if you can see it, there's a red annotation on my screen, but anyway. Did I draw that by mistake or something? Oh, anyway. So this is an example of exactly doing what we were saying before. So if you imagine, we've got in the top left, we've got an input image. We do some convolution. So we generate all these abstract features from our input image, and it's not up to the person who's developing the network to decide what these features are. They're just learnt by the computer. Sometimes those, by reverse engineering, you can see what those features, what their properties are. So it might just be like one of the features might be sort of how dark the image is, or how speckled it is, or how much the light is to the right hand side of the image. But I mean, they're generally sort of, as I said, defined by the computer. So, you know, it's very difficult to kind of to say. But by learning associations with those features, you know, we can do classification tasks. So in many respects, you know, the convolution operations that we were talking about before, they're essentially encoding the input image. So that they're turning it from a large set of, you know, input pixels into a much smaller set of sort of, you know, abstract features. So, you know, and they're kind of encoding the information. So think of an analogy a bit like, you know, if you want to sort of make a cake, you could think about, you know, all the sort of atoms in the cake as being, you know, that's the kind of raw information. So to decode that, what you'd essentially do is turn that into a set of ingredients, you know, half a pound of flour and 3 eggs or whatever, and then a set of instructions for, you know, how to mix these ingredients together. So you've essentially reduced, you know, what was a huge amount of information to a much smaller amount of information that is capable of generating, you know, it's capable of encapsulating the kind of information in the input. And, you know, by the same analogy, you know, decoding it is then turning those ingredients and those set of instructions into the cake. So, and that's what you do with something like segmentation. So we take those abstract features and then we do the reverse of the convolution. So we do this deconvolution. So we turn abstract features into, you know, pixels. So the output in that case is an image of some sort. Usually what we've done is essentially we've removed all the information we're not interested in and just left information that relates to the, you know, classes that we're trying to segment. So you can see here that, you know, you could, with the same set of features, you could either classify the input image or you could segment it, or you could do both using the same set of features. Okay. So that's really, yeah.
There's follow-up questions on that, or two of them actually. What is the pros and cons for the combining those like multitask into one engine?
Yeah, good question. So I would say that the pros are that that you can essentially use the label information from one, you know, set of labels, or you can combine the labels for two different problems to, so that they help each other with the training. So, you know, you might have a small number of segmentation labels, but a lot of classification labels. And by training them together, you probably get a much better segmentation than you would if you just use those segmentation labels, because the classification has probably taught it a whole load of features which are actually quite useful for segmentation as well. The downside can be that, you know, it can be more difficult to train because you're ending up with a network that is probably a little bit more complex than it would have been otherwise, and maybe a bit more complex to, you know, to sort of architect. So that's the, and it's probably a little bit less standard too. So, you know, you'll find loads of information on how to deal with a network that's struggling to train if it's just a plain ResNet or something. But if you've customized it to do something else a bit more exotic, you know, you may find it a bit more difficult. And of course, the other thing is at inference time as well. So if you deploy it, you know, if you've had to deploy multiple models, that may not be terribly efficient. If you can combine them into one that does, you know, outputs everything you need, you know, that could reduce latency and reduce the amount of, you know, computation needed. Okay.
You want to take another question?
Sure. Yeah. Why not? Yeah.
So comparing to traditional approach and between the traditional approach and deep learning, as we omit the feature engineering phase to some extent, don't we need larger data set to compensate it?
Yes, that's a very good point, and the answer is yes. We do. In general, we do. Deep learning is very sort of it's very data hungry, so you need a lot of examples to train it robustly. That is very true. There are some shortcuts, of course, you can take these days. So, for example, you can use a pre-trained network. So, if you want to train, let's say you've got a fairly small data set of MRI images of the brain or something, and you want to pick out a particular pathology or something. Now, if you're doing that from scratch, yes, you might need hundreds of thousands of images or tens of thousands of images to do it. But if you use a pre-trained network that has itself been trained on, thousands of images, and they may not be solving exactly the same problem, but that can massively reduce the amount of data you need to then, fine tune this model for your specific problem. So it's kind of less of a problem than it used to be. And of course, the other thing which is really very, very popular at the moment is this, these semi-supervised learning techniques. So there's lots of different ways that this can work. But one good example of this is, so it may seem slightly sort of odd, but I'm sure many people have heard of things like variational autoencoders. So this is one type of network, and what it does essentially, if you look at the image we've got here, it essentially takes the input image, does all these convolutions, creates these small number of abstract features, and then what you can do is you can train it to then regenerate the original image. And so the label is actually the input image. So so what you're doing is turning this input image, you're encoding it essentially, and then you're decoding it. Now it may seem a bit pointless to do that. Why would you train it to do? I mean, it can have some practical applications. So one practical application of that is compression. Or noise removal. So you can, create a much smaller sort of compressed version of that input image and then reproduce it quite faithfully from a very small, piece of sort of variable information. But what's interesting about that is that when you've done that for a large number of unlabeled data, you will typically have ended up with a whole load of really useful features that the network has learned. So if you then do the sort of, the classification bit on this image, so you're then just training it to classify something with maybe a small number of labels, because it's learned such, really good features. From a large amount of unlabeled data, then again you massively reduce the amount of data you need. And there's another topic I'll save for later as well that I'll refer back to on that point too. But the short answer is yes, and the longer answer is not quite so much as you used to. Okay, so far was there another question as well, or shall I move on for now? Okay, I'll move on.
Yeah, please move on. Yeah.
Okay, good. So those images we talked about so far, mostly for image processing, computer vision, and there's lots of very sort of mature networks that are widely used, things like ResNets for classification, to be honest, the fundamental architecture of those networks for sort of computer vision hasn't really changed a huge amount. There are some new variants around, but most of the innovation is not particularly in those areas. There are other areas where innovation seems to be going on. I'll cover that at the moment. So I'm sure many of you are familiar with recurrent networks as well, which is a slightly different use case. They tend to be more for sort of dealing with with sequential data. They don't have to be at all. They can work perfectly well on images too, but they're just sort of, you know, I guess the typical use case these days is probably, you know, natural language processing, that sort of stuff. So, and there are lots of different examples. So you can get these kind of, you know, one-to-one, where you've got fixed sized input and a fixed sized output. So, you know, image classification might be an example of that. Then you've got these kind of sequence output versions, this sort of one-to-many. So example of that might be, you know, you have a single input image and the output is a sequence of words, which, you know, maybe a caption for that image. We then have this kind of many-to-one where you might have the input, let's say, might be a paragraph of text, and then the output is just you know, a value which represents how positive or negative the sentiment was in that, you know, so sentiment analysis. Then we have the sort of many-to-many, so like machine translation is a good example of that, where, you know, in many different languages, the number of words is not the same, so you need to have a sort of, you know, variability in the input and output. And then finally, we have this kind of many-to-many where you might be doing something in real time, you know, maybe classifying videos, you know, frames in a video. So there's a kind of one-to-one relationship between the input and the output. The original motivation actually for well, no, I'll carry on. I'll get to that in a little bit. Okay, so how do they differ and how do they work, these recurrent neural networks? So they, so if you imagine the green sort of inputs, for this kind of sequential information, so imagine, you know, they are words in a sentence or something. At every time step, you ingest a new input, and then you apply some sort of weights or set of weights to it, and then you produce some output, and then you carry over this, you know, these output values into the next iteration, and you apply more sort of weights to it, and you basically just repeat this multiple times. So there's a certain kind of simplicity towards this, and the weights, just think of this as a very sort of simple, very simple sort of neural network. Essentially, that's what it is, doing some sort of matrix multiplication. I'll go into the details of that a little bit more, but so if you imagine, you know, for the purple is our input now, and then the green is our output. So what we're doing as we're stepping through the input is we're keeping some information from the previous step, and then we're sort of combining that with our new input to make a new prediction at each time step. And typically with these recurrent neural networks, that you have a fixed number of time steps that you are able to keep, and that unfortunately is their downfall. Is that, you know, well, there's a couple of things. So one is you can't really have an unlimited number of time steps that you can keep. The more you have, obviously, the more memory it takes up. But also, the more you have, the more they have a tendency to forget information that happened, you know, a long time ago. In a, let's say you've got a very long sentence or paragraph. So that is a problem. And part of the reason behind this is this idea of the sort of vanishing gradient problem. So so with vanishing gradient, so I'll just step back a minute. With vanishing gradient, what happens is, because we're carrying over these weights every time step, every time you apply these these weights, we're essentially doing a multiplication. Now, if you imagine, you know, the way that, for example, compound interest works, over a period of time, things tend to sort of steadily grow, or if you're, you know, multiplying by less than 1, they tend to steadily shrink. And that is exactly what can happen with these things, that you can start to get this vanishing gradient problem where, you know, after a few iterations of multiplying, all the values just end up near 0. and some of the more recent networks seek to address that, but this is this sort of, you know, vanishing gradient problem. The other interesting thing about these recurrent neural networks, you know, stepping through a time sequence, and this is remarkably like a you know, a Turing machine for anybody who's interested in this, and actually, you know, some work went on to validate the fact that recurrent neural networks are Turing complete, so in the sense that they can simulate arbitrary programs, which is, yeah, interesting little snippet of information, I suppose. But like I say, they have their failings, and so what that has really motivated is this new breed of networks which use this attention sort of mechanism. So this was one of the sort of seminal papers that motivated a whole load of sort of interest in this idea of attention. So what was proposed here essentially is another type of network that is also kind of good at dealing with sequences, but it does not have a sort of fixed number of previous sort of iterations. And also the other problem actually for GPUs is that GPUs are very good at doing stuff in parallel. And if you have to ingest a sentence word by word, essentially, you know, that is then a sequential operation, which means it's quite difficult to get it to work efficiently on something like a GPU. With these attention networks, these sort of transformer networks, what they do is they kind of remove that need to have this sort of fixed input vector, and the way they do this is by essentially sort of figuring out which parts of the previous input are important and which aren't, and they use this attention sort of mechanism. It sounds, you know, it's pretty much what it sounds. I mean, in as much as if you've got a long sentence, there are certain words that are more important than others for predicting, you know, let's say the next word in the sentence. So you need to you know, if you've got the word sort of he in there, you need to look back to the, you know, who is this the he that we're talking about. So you typically need to look back to, you know, maybe there was a name a few words previously. So this is exactly what attention does, is it says, well, to figure out what's next given the previous words, these are the previous words that were the words before that were more or less interesting. And you can do the same thing with images as well. So if you think about it, you know, for something like pathology images, which are, you know, these huge images, you know, you really need to, when you're making a diagnosis as a human, you need to be able to figure out where the important information is and not, you know, spend time looking at all the other bits, because there's no way you could, because this is a whole slide image here. And on the left-hand side, you know, this is the sort of size of a, you know, full HD or ultra HD screen. And if you project that onto the whole slide image, you can see that it's a tiny sort of piece of it. So how, you know, there's no way a human could look at every single sort of piece of this image, and that's not what they do. They look at you know, a low resolution version of the whole image, and then they zoom into certain bits of it which they think are more or less important. You'd actually need, I think it's over 2,000 4K screens, or no, sorry, 4K full HD screens to be able to view this at full resolution. And you know, a pathologist will probably be looking at I don't know, maybe 20 of these for a particular case when making a diagnosis. And you know, this poses a similar challenge to the computer as well, because that's a lot of data to crunch. Another way of putting it is, if anybody's worked with a CIFAR-10 data set, all 60,000 CIFAR images in that data set fit into a box that size on a single whole slide image. So yeah, and so this just reinforces this idea that that's not, you know, we need to be able to focus the algorithms on the parts of the input that are important, because otherwise it's just an overwhelming problem. And the way the mechanism that does this is very, very simple. It's just this gating mechanism. So you essentially, if you have an input, let's say on the top, we've got these 3 boxes, and imagine this is a single pixel input. So we've got a red and a green and a blue channel. We've got these 3 channels. The red is, value 1, so is the green, and the blue is value 0. So to apply a weighting to this, we're essentially just doing a multiplication. So in this particular case, we're just, the output is we've removed the red information from this just by, because it may well be for this particular problem, whatever it is, red light is just not important, but maybe green and blue is. So this is essentially how weighting works, and the network is essentially learning, what value to multiply the inputs to. And it just does that. So that's how the attention works. And it also has the benefit as well of being differentiable. So for anybody who knows about the way that neural networks work, when you're training it, the operations need to be differentiable. So if you have conditional statements in there which say, don't look at this part of the image, that's not going to work. You can't really train on that. Whereas these attention mechanisms, where you're basically, getting it to learn how much to turn on or off certain inputs, that is a differentiable operation. So that's kind of how it works. Now this looks very complicated. This is an LSTM module. But what I wanted to just highlight is that in the middle. So the LSTM has these units, and essentially what they're doing is applying this attention mechanism in a. So if you look at the 2 green boxes in the middle, what that is actually doing is that is applying attention to the inputs at a particular time step. So it is you can see a little network, and that network's job, all it is doing is just learning how much to turn on or off the inputs. So it's basically it's multiplying them by a value between 0 and 1, which is why it has this sigmoid activation. And it has LSTM. So what it does, it has a sort of it passes information from one module to another in a sort of recurrent network, and it tells it which information is important for this current time step, which information is kind of stale and you can ignore now. So it uses this exact same very simple sort of multiplication mechanism, and by doing this you can resolve some of these vanishing gradient problems, because you can pass information on that's important and turn information off that is no longer important or not important in the current context. And the other thing is that so with these transformer networks, the sequence is no longer actually important, so the order of the words isn't. Now, in fact, it learns its own, it just learns its own importance, which typically is, does have a sequential element to it. But you can see here in this sort of machine translation, if you look at the attention between, different words in the sequence of the sentence, it's not linear, because, and then, in the different languages, the order is slightly different, but the network will just learn that sort of naturally. It's not, the sequential bit is not sort of assumed. And you can see in this image captioning example how the network is learning to focus on particular parts of the image for particular sort of words. So when it's considering the sort of frisbee bit, that you can see where information has been turned on or off on the image using this attention mechanism.
Yep, Jonny,
Yeah.
there's a couple of questions, and we have about 35 minutes left.
Okay, great.
Yeah. So this could be interesting questions from Huang Le, NHS Digital UK. So the question is, in healthcare, what is the best way for us to iterate and update the algorithm when more data coming in, or the doctor validates some of the difficult cases?
Right. Yeah, that's a good question. So, so there's some really important points that raises. So one of them, of course, is the fact that if in a regulated environment, which obviously healthcare is, at the moment, for an algorithm to be approved, it has to be approved for a sort of fixed function. So today, you can't have an approved algorithm that can be updated on the fly as new information comes in. So the only way that could work is obviously that whenever something like that happens, that any exceptions are then maybe fed back to the algorithm developer for them to use next time they retrain the algorithm, and then they'll retrain it, and then it will have to be reapproved, and then when it's been revalidated. Now that's a very long-winded process, but that is the way it kind of works with FDA and CE approval today, for safety reasons. That everything has to be sort of validated. Now that may change, and of course the other thing is, in reality, there are a lot of research hospitals out there where individual clinicians do have the ability to do sort of online training, but it's it's their responsibility to kind of make damn sure that those predictions that they're not relying on them without unnecessarily sort of thing. So you can do that, and of course there are many use cases in healthcare which are not quite so safety critical, in which you could do that. So there's a lot of stuff which is which is not going to be sort of dangerous, like predicting whether somebody doesn't show up for a radiology appointment, let's say. Now it may seem a trivial use case, but that sort of stuff can be done, and is done, and can save hospitals a lot of money. So so you could do that. You could use online learning for that, but for radiology, you tend to, like I say, just sort of log. A user would just log any deficiencies with the algorithm, and then it's really up to the algorithm developer to find a better training data set, so maybe to cover those cases that it's not predicting very well. I think that will change, but no one's quite sure how. But yeah, interesting question there.
I like that how you stress the make damn sure. Just reflects how conservative the healthcare section or sector is.
Yeah, and I think the reality is that what will happen is that you will have algorithms that are live and fully validated, and for which they're fully audited, and they're safe. You'll then have another tier of algorithms that have not yet been fully approved. So they've been tested, but they've not been fully approved by, let's say a particular institution. So they'll probably run them in the background. And maybe, clinicians will be able to take a look at what that algorithm would have predicted, and maybe provide some feedback for it. But it would, but that's in the sort of validation phase, if you see what I mean. Only when that has then reached a certain threshold of safety would it then be allowed to be used, by anyone, sort of thing. So,
yes.
Okay. So
and I think we might need to speed up a bit, but then I will also have a quick question here. With when you present this gating slide, what is a difference to the weights?
What's the difference between the weights? Sorry.
So when you say about the gates, then what's the difference between gates and weights?
So there is no there is no difference between them. They are the network is learning weights. It's just that those weights are being used to essentially turn information on or off. That's the only difference. So yeah, but there's fundamentally they're not. You know, it's a bit like it's really just turning on whether features are important or not. So you get this, imagine you get this idea of like self-attention, for example. So you might have a module that accepts an input and at the same time is able to say whether that input is important or not, and then weight it you know, by importance. So yeah, there's nothing fundamentally different about this from any other sort of weighting. It is it's just really learning to turn information on or off. It is a simple sort of concept, but it's just done in a sort of, you know, it's quite a complex sort of network architecture to do this in conjunction with everything else. Okay, so I'm going to crack on because, as you say, probably I should. So how long should have I got for the sort of talking bit? How much longer?
We have 27 minutes left,
okay,
according to the schedule. Yeah.
Okay, that's great. All right, so I want to cover generative adversarial networks next, which a lot of people have heard about. They're very interesting, and there's a lot of, you know, a lot of use cases and a lot of interest in this. What probably most people, you know, is not necessarily immediately obvious is why they're important in healthcare, you know, because I think most people who've seen them have probably seen them, you know, creating deep fakes or, you know, that sort of stuff. But they are actually incredibly useful for a number of different things. So, for example, generating, if you have, quite often with medical data sets, particularly for rare cases, we don't have a huge number of training examples. So one thing you can use GANs for is to generate artificial examples. So, you know, you can basically increase your data set training size by supplementing it with artificial images. So that's one use case, because you essentially train it to you know, to be able to reproduce or to produce images that are quite realistic. Just very briefly as well, I'm sure most people are aware of this already, but the way that the generative adversarial networks work is you essentially have two networks. The analogy to think of here is a bit like imagine that one of the network is like a forger and it's trying to forge banknotes, and the other is a police officer, you know, police detective, who's trying to spot forged notes or not. So when both of them start off, you know, probably the forger's not that good at it, and it's quite easy for the policeman to say that one is not real. But so he has to up his game a bit, the forger, and actually starts producing these ones that are, you know, pretty good. At which point, you know, if he's able to fool the policeman, then that's good. But if the policeman finds out, then he's going to look even more closely and then probably find some little sort of difference that he hadn't noticed before. And this will obviously go on and on and on until you reach the point where well, just go on forever essentially. The forgeries basically get better and better, and that's exactly the same principle as is used here. So an image generating network can generate a sort of image from random noise essentially, and then the discriminating network will either say is it fake or it's real. If it says it's fake, that gets fed back to the network, which then adjusts its weights until you know, it slowly starts to improve. And equally, if it fools the discriminator, then the discriminator updates its network to make it better at finding them. So this is how it works. And you know, this is just a very simple example, but just showing you a very sort of low resolution training of a generative neural network. So I think it's cycled, there you go, just recycle there. You can see it starts off with these sort of very mottled sort of cubes, but very quickly it starts to produce something that looks vaguely like a sort of brain MRI. So that's the principle behind it. But it's also very good at doing things like image segmentation as well, because if you provide it with, you can get it to not just take a sort of random generate an image from random input. You can also feed it an image and then get it to output an image of a different type using exactly the same training process. So if you don't have a label or many labels, you can train it to generate realistic looking labels, and the other way around as well. And then you can start doing some really interesting things, because let's say you've got an MRI data set with a lot of labels for a particular type of tumor, and you've got a large CT data set, but you don't have any labels for it. You can use something like a GAN to translate the labeled MRI images into labeled CT images, and then you can, then you've got a training data set you can use. So this stuff's actually incredibly useful, and there are lots of complicated ways you can use them, creative ways that they've been used to, in this particular case, generating artificial tumors to improve data sets. There's a few other ones as well. So bottom right there these are the fake celebrity faces which you'll have seen. So these are generated by GAN, so incredibly realistic. The top left is an interesting one. So this one here, you've got these 3 brain images. So what you're looking at there, on the top left is a standard dosage of this gadolinium, which is a contrast agent, and it picks out the tumor. So where the yellow line is, you can see there's a sort of slightly lighter area, which is a tumor. And in the middle image, you can see the same image where the person's only been given a 10% dose. And the reason why you would want to do that is because this stuff is it's a chemical that has unknown side effects. Obviously, if somebody's ill enough to have a tumor, it warrants giving them this contrast agent. But ideally, you want to reduce the amount of chemicals we put in anybody. But you can see that with 10% of the standard dose, it doesn't show up. It's the same contrast as the background sort of area. But you can use a GAN to learn to enhance that image, to reproduce the original image with the standard dose from only 10% of the contrast agent, and with a quarter of the scanning time as well. So it's actually a lower resolution image that is then learned to upsample as well. And that's also the way that, for example, that the ray traced images, you can see the abdomen and the restaurant. They use ray tracing, and ray tracing is the same thing. So from a low resolution image, you can train a generative adversarial network to fill in the details for you, because ray tracing is actually computationally quite expensive. So another really important thing. So we have a group of Kaggle grandmasters at NVIDIA, and all they do is enter competitions. And they were kind enough to speak to our pathology group recently, and they basically told us that there are 2 things which they do which are really important to winning a Kaggle competition. One of them, and it's not what you'd think. So they use all the standard networks that everybody else uses, like ResNets and UNets and whatever it is. Where they make their gains are in 2 areas. One is ensembling. So ensembling is where you don't just train one network, you train, let's say, 10 or 15, because the training process is random. And so every network you train will have very slightly different, strengths and weaknesses. So by pooling all those strengths and weaknesses together with some sort of voting system, you can actually usually get a little bit more accuracy. So, and this is often done to try and beat the competition with these sort of Kaggle things. In the real world, it's not really done that much, because you're probably talking about sort of 0.1% accuracy improvement by using 10 networks rather than 1. But it is used nevertheless, and when you think about it, ensembling goes on inside these networks, because you've usually got a lot of neurons, a lot of features, and they're all sort of, there's usually quite a bit of overlap between what they learn, but there's a kind of sweet spot of the amount of redundancy and the amount of accuracy that you tend to sort of end up with. And the other one is data augmentation, and this again comes back to how you can increase your data set virtually, if you like. So obviously you have to be very careful about how you augment data, because for example, if you flip someone's brain, that might not be a sensible thing to do, because the left hemisphere and the right hemisphere are different in some ways. But so you have to be careful about how you do these transformations, whether it's a valid thing to do or not. But in every domain it's different. But typically you'll be doing things like rotations and flips and shears and scaling and adding noise, and this makes the network a lot more kind of robust. Okay, so just very quickly as well, I just wanted to mention that, and I have touched on this already, it's not just about deep learning. There's a lot of other stuff that is going on in the machine learning space, which is also AI, but it's just typically working on kind of more structured data. So and there's lots of really important kind of use cases. So I mentioned things like predicting sort of, I don't know, risk of sepsis or whatever, just from mining sort of more structured information in patient notes. Yeah. So yeah, lots of classical machine learning use cases that are out there too. So one last sort of big topic I wanted to talk about was, which I'm not going to spend a huge amount of time on, but is federated learning. Just what, why we need it and how it sort of operates. So with medical data, it's very difficult to get hold of large amounts of it. And the other thing is, if you're a small hospital, you probably haven't got, as much data as you possibly need for deep learning training. But sharing data is fraught with all sorts of, ethical and legal and data governance challenges. It can be a really difficult thing to do. So federated learning, what it essentially does is the data doesn't leave the institution in which it's kept. Instead, what you do is you do some training at lots of different hospitals with the same model. Let's say you do 2 or 3 epochs of training, then you pass that, you either pass that model around, or you send it back to one location and you aggregate it, and then you send it back out again. And by doing this, everybody can basically benefit from training in a way that essentially mimics if all that data was at the same institution. This is being used in quite a few domains now, but healthcare is being one of them. We've done some studies trying to prove this. So we've done one recently on predicting whether patients would need oxygen support, COVID patients, and the input to this was X-ray images and clinical notes. And yeah, we did this across 8 different countries, 20 different institutions. And the model that was produced, that was learnt, was more accurate than any of the models that any of the individual institutions. And there's a paper in preprint on this at the moment. But yeah, this is really sort of promising field. As I said, there are lots of different ways of doing it. You're always either passing around the weights or the gradients. Usually you add some noise to it just to prevent any possibility that somebody could reverse engineer any data out of those. I mean, it's very difficult to do. It would be very difficult to do anyway, but this just adds some more protection to it. You can do it sort of peer-to-peer, so you can just pass the model weights around different institutions, or one of them can act as a sort of aggregator, or you can have all sorts of hybrid architectures where maybe in one country you have some sort of peer-to-peer training, and then you exchange that model with other countries. So there's lots of different ways of doing it, and King's College in London are sort of we're working quite closely with them on. They're doing it across about sort of 8 different hospitals in London, sort of routinely. I'm not going to spend too long on this given the time, but obviously, as I said, there's lots of different challenges of this, and we've kind of touched on some of them. There's sort of bias in AI. You've heard a lot about this. There's safety. There's implications for changing kind of workplaces. People's roles changing. And it's something we definitely all need to be aware of and think a little bit about, and particularly there's things like sort of bias. They are things that we can control, and privacy as well, and this is no more so than in healthcare, and it makes it a lot harder. In other areas you can just get on and do things. In healthcare it's really difficult to get through this, the sort of moat, across the moat of regulation and patient safety and patient consent and ethical approval, which is why it's kind of taken so long for the AI to really sort of take off in healthcare. Also, just like the healthcare trust, building up confidence takes a long time, and it is growing, but it can take a while. The other thing is, another really important thing for deep learning practitioners is that we tend to train on ideal data sets, and in the real world you don't get that. You get these low contrast, low resolution images, or even things which the computer was never trained to see, like you need to make the networks robust against these sort of outliers, and people often forget to do that, and then the network trips over and produces some nonsense prediction, which then reduces confidence in the ability. So this is a really important thing to do. Couple of other things before I sort of wind up this bit. So computational drug discovery, another massive sort of area that uses a lot of things like transformers, natural language processing as well. They do a huge amount of that, mining all the sort of literature. So I want to talk about some of the latest tools. I'm gonna skip over this video I've got here just in the interest of time. We've got, so yeah, natural language processing, like I said, that's a big sort of thing. We've got a medical imaging toolkits called Clara, and also an open source variant of that called Monai, which people can download and use. And it just does a lot of the sort of things which anybody who's doing deep learning in this space will have to do themselves, like loading DICOM images, getting them into a NumPy array, these sorts of things. There should be no need for everybody to have to do that. So I'd encourage you to have a look at Monai, this open source. So we're doing a lot of stuff in genomics, so I haven't covered today as well, including deep learning stuff as well, because obviously finding associations, that sort of stuff, on the massive data sets of genomics is really important. We're also doing a lot of sort of real-time streaming type stuff. So ingesting video information to detect whether patients are still breathing. Funny enough, you can even detect things like their sort of heart rate and breathing rate from video. Check whether they've detect whether somebody's fallen over, safe social distancing, body, all these sort of real-time use case stuff that's getting very popular, particularly in the kind of COVID era. So the last piece is how to get started on this. So very quickly, there's a couple of things I want to mention. One is having this sort of project checklist. What are the problems you're trying to solve? So think, have a think about, when I was talking before about, is this a segmentation problem? Is it a detection problem? And therefore, what sort of type of network might you need? And how much data have you got? And has it been labeled? And if it hasn't, how are you going to get it labeled? Again, what about the sort of choice of tools that you're going to use? Is that sort of been decided or not? There's lots of different sort of things to think about. Now, ideally, we would all have one of these on the bottom right, which is a Cambridge One AI supercomputer that's recently been announced, that we're just kind of working on at the moment. Now, obviously, not everybody's got access to something like that. So there are a few lesser resources. I'm just gonna, let me just skip over this. So just want to highlight a couple of other things. So yes, things like the A100 Ampere GPUs are built for sort of deep learning training and inference, and they're very kind of flexible as well. You can divide one of these up between 7 different users, some of whom might be training and some of whom might be doing inference. And there's a lot of the whole load more are just about to be announced at our GTC conference, but you can see this sort of range of GPUs for different tasks. The other thing which is very popular, increasingly popular in academia, is DGX systems. So you've got 8 of these Ampere GPUs in a box to make this kind of deep learning supercomputer, and that's what this Cambridge one is built out of 80 of those. We also have this Deep Learning Institute. This is a really good way to get started. So academic institutions can sign up to be able to get free online access to the courses that are on there. So there's this kind of fundamental ones. There are a few healthcare things on there as well, and lots of other domains. So please reach out to me if that is of interest to you. The other thing is, so this is a massive one actually. I want to definitely highlight. Oops, just want to highlight this one. So we've got our GTC conference coming up in a couple of weeks, and I would very much. It's free to register, and there are about 1,500 different lectures on all sorts of healthcare topics and other industry topics. What I'm going to do is try and just get that URL and put it in the chat so that you can register, because like I said, it's free and you can watch these videos at any time as well. So I think it's well worth doing. There's some really exciting talks on there. We've also got our CEO is doing like a fireside chat with some of the fathers of AI, like Joshua Bengio and Jan LeCun, Jeff Hinton. These sort of luminaries. That should be really interesting too. But there's loads of healthcare stuff, so I think that would be well worth doing. When I've stopped showing my screen, I'll copy that into the chat.
I can and also quick question, Jonny, because there seems to be many interested in having the slides and also the recording of this video. I will send out the link to the video later in a couple of days when I finish uploading. But also, would you be able to share the slides and so I can send to them? Yeah.
I can do that. Yeah.
Okay, thank you. Great.
So I think it's probably just worth one other. I'm just going to finish off with one short video that I think is could be quite interesting. So this is a new product that is just kind of coming out, and it's called Clara Studio. So we've got this Clara Healthcare AI product. What we're doing is creating a sort of graphical user interface for it. So you will be able to download this for free from our NGC site, which I also am happy to share some info on that. I think it's in the slides anyway. So let me just play this. Hopefully you can hear audio.
Building an AI model typically involves the following steps. 1, annotating the data. 2, training the model. 3, evaluating the model's performance, and then repeating the above steps until you achieve good performance. Clara Studio includes all the tools you need to get started with training a deep learning model for healthcare. It includes the open source OrtHanc DICOM server and the OHIP medical imaging viewer enabled with NVIDIA Clara's AI-assisted annotation capability. And for more advanced users, it also includes Jupyter Lab with interactive example notebooks and, of course, a shell terminal. To kickstart things, Clara Studio includes a list of publicly available datasets that you can quickly download. If you have your own dataset, you can simply import it into Clara Studio. After you've downloaded or imported your data, you can explore the images through the built-in web-based viewer. If you need to apply some transformations to the images to prepare them for training, you can quickly do so using the pre-built Clara transforms. If you need to annotate some fresh data, you can do that as well using NVIDIA Clara's AI-assisted annotation plugin inside the OHIP viewer. Using NVIDIA pre-trained deep growth 3D model and AI-assisted annotation, even 3D segmentation of organs is as simple as a few clicks. Once you've finished annotating, you can save the results and start training. Clara uses the standardized format to define deep learning models called MMAR, Medical Model Archive. An MMAR packages pre-trained models along with transfer learning scripts that make it very easy to train top-performing models on your own data. NVIDIA provides dozens of free pre-trained MMARs through our software hub called NGC, and are readily available for download and use from the MMAR page in Clara Studio. We went ahead and downloaded the spleen segmentation MMAR and can use it to train a new model on our spleen dataset. Since you've already annotated your data, you're ready to train the model. You simply select the MMAR and click to train.
I'm going to stop that there, but I think you get the idea that this makes it incredibly easy to kind of get started. That's on YouTube, I think, so you can take a look at it. Yeah, that's pretty much everything I wanted to share. There's probably a few other bits and pieces on some of the slides I didn't show if anyone's interested. But yeah, any other sort of questions in the remaining time?
Yep. I have a question. Can you hear me?
I can't quite hear you. I lost you, but so I'm just posting the link to the GTC registration. If you click on that link, it'll take you to the way you can register for our all those free videos on the conference. Clara Studio costs. Clara Studio is free. All our NGC stuff is free to use. You can just download it and use it. Clara is not open source, but MONAI is. So MONAI provides a lot of the sort of fundamental routines that we use. So if you want to build your own Clara, you can use MONAI. If you just want to use, what we provided, then just download Clara and use it. There's a training piece to it and there's a deployment piece to it. It's probably the train one that you'd start off with.
Yep. Yes, thank you, Jonny. It was great presentation today. So there are a couple of questions more, and I will send you via email, and then I'll post the answer on emails and on the Facebook page.
Yeah, great.
Yeah, I think, and sorry for not being able to handle all the questions, everyone. It has been a great pleasure to have you here today, and also to have Jonny with us and discuss this very interesting topics. And yes, time's up for today, and yeah, look forward to see you next month. We have it every month. So yeah,
thank you very much,
and enjoy the Easter and Easter vacations if you do have, or yeah, enjoy the rest of the week. Thank you for today.
Thanks a lot. Yeah, nice to talk to you all, and yeah, do send questions. I'm very happy to answer them.
Great to hear.